Hello everyone. In this video, I'll introduce our project, Puppeteer, which enables automatic rigging and animation for 3D models. With our method, you can control your 3D models just like a puppeteer. Recently, 3D object generation has been advancing rapidly. Platforms like Clay, Tripo, Hunyuan 3D, Meshi, and others can generate impressive geometry and textures. But these objects remain static. So what's next? How can we build upon this progress? We believe the next step is bringing these 3D objects to life. We can achieve this through rigging and animation. This is our pipeline. Given a 3D model, which can come from text to 3D or image to 3D generation, we first perform automatic rigging. We then render the rigged mesh as the initial frame and feed this image, along with a text prompt, into a video generation model to produce an animation video that guides the 3D animation. Finally, we optimize the 3D animation to closely align with the generated video. First, let me introduce the rigging component. Rigging requires two key elements: the skeleton structure and skinning weights. Skinning weights define how mesh vertices deform in response to skeleton movements. With these components, we can animate 3D models using linear blend skinning and other deformation techniques. To train our auto-rigging model, a large-scale dataset is crucial. Here are key statistics from our dataset, Articulation XL 2.0. The dataset is dominated by character models, approximately 75% creatures and 25% non-creatures. Bone counts range from 2 to 100, with the most common configuration being 52 bones, which aligns with Maximo rigs. We've released Articulation XL v2 with over 59.4K models. In comparison, the previously largest dataset from RigNet contains fewer than 3K samples. Our dataset is approximately 20 times larger. Beyond the 48K samples from Obgiverse XL, we conducted dataset expansion to address a key limitation. We observed that most Obgiverse XL data are in rest poses. For example, human models are typically in T-pose or A-pose configurations. Consequently, models trained solely on this data may struggle with diverse pose inputs. To address this, we created a diverse pose subset containing 11.4K additional samples. These dataset expansion significantly improve generalization to diverse pose inputs. Now, let me introduce our rigging network. Our system first predicts plausible skeletal structures using an autoregressive transformer. This transformer incorporates a joint-based tokenization strategy for compact representation and employs a hierarchical ordering methodology with stochastic perturbation to enhance bidirectional learning capabilities. Next, our system computes skinning weights through an attention-based architecture. The key feature is topology-aware joint attention, which explicitly captures interjoint relationships by leveraging skeletal graph distances. For video-guided animation, the inputs are a rig model and a generated video with n frames. For each frame from 1 to n1, we optimize the root motion, including rotation and translation, as well as per-joint rotations represented by unit quaternions. We do not optimize frame 0 since it serves as the rest pose with 0 translation and identity quaternions. Our optimization incorporates multiple loss functions, rendering losses, tracking losses, and regularization terms for motion smoothness. Now, for the experimental results. These skeleton generation results on AI-generated meshes show Puppeteer's performance compared to Magic Articulate. While our method produces well-aligned skeletons, Magic Articulate struggles with alignment, particularly visible in the dragon's tail and deer's leg positioning. It also loses fine details, such as the bones in the tail and wings, as well as the robot's hand structure. In contrast, Puppeteer consistently generates valid, well-structured skeletons that preserve these important details. For skinning weights, we compare our method with RigNet and Magic Articulate. While Magic Articulate's functional diffusion performs well on the main dataset and diverse pose subset, It degrades significantly on model's resource due to limited cross-dataset generalization. In contrast, our method produces consistently accurate skinning weights with lower error rates across all datasets. Here are the animation results comparing our method with L4GM and MotionDreamer. While L4GM's reference views align well with the source video, the method suffers from geometric distortions. MotionDreamer produces subtle animations and introduces unintended deformations in rigid parts, such as the turtle shell. In contrast, our method generates more accurate animations with our generated rigging. Thank you for watching. Please scan this QR code to visit our project page for more details and resources.